Well, I want to start out with a pre-class quiz this time. What's wrong with this C program? Let's look at that. So it says int main, and we have unsigned character I and sum 0. So I and sum are both characters. Those are 8-bit numbers, by the way. Car is an 8-bit number. So it says for I equals 0, I less than 1000, I plus plus. Sum equals sum plus I. Wonder what might be wrong with this picture. Well, let's think about this. A character can only have 8 bits, right? So the highest number, if it's an unsigned character, would be 255. Wait a minute, 1000 is bigger than 255, and furthermore, I'm going to be adding sum to I. Well, fortunately, sum is 0. But we still have this problem of I is going to overflow. Oh, sum is sum plus I, so it starts out at 0, but it gets bigger and bigger and bigger. Oh man, this is really going to be bad. It's kind of like what's wrong with this picture. You know, it says 45,247. Yeah, I wonder if it's 145,247. Wonder. Okay, so let's look at some fractional data types. Today we're going to look at a way of representing numbers that have fractions in them. And the simplest way is called a fixed point number. And basically, in some way, what we've already been doing is a fixed point number, but the decimal point was fixed at the end of our binary sequence. But we could move the decimal place somewhere else. Like normally we have our decimal point right down here, and this would be 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, 2 to the 7, and so on. But now what we did was we moved it over so that 2 to the 0 was right here. That means all these yellow things are actually fractional part. So this 1 means 2 to the 1 times 2 to the minus 1, and all the others, are 0 times all those different powers. And this 1 means 2. Well, 2 to the minus 1 is a half, and 2 to the 0 times 1 is 1, so this is 1.5. Now, the nice thing about this is now we can use get more precision about fractional numbers. In general, in fixed point notation, the program is responsible for knowing the position of the decimal point, and you can do this with signed or unsigned numbers as you wish. It requires less processing or resources than floating point, which we'll talk about a little bit later. The decimal point is fixed. In this case, it's always 1, 2, 3, 4, 5, 6 places to the left of the least significant bit here. Okay, so with a fixed point fractional part, we can have fractional numbers, which is nice. The more bits you use in your fractional part, the more accuracy or smaller number you can accurately represent. You can use 2's complement for negative numbers. The accuracy or the precision really is 2 to the minus number of fractional bits. And if we take an example, if we have 6 bits, our fractional part, like the above, our accuracy is 2 to the minus 6, which is 0.015625 if you put it in your calculator. In other words, every bit is equal to 0.015625 of a unit. The integral part is the yellow part there, and the fractional part is the white part. So for fixed point addition, you just line up the decimal points and you just add just like you would normally. If you you know, did this thing without fixed points, you wouldn't get the right answer. Here you get 5, adding 2.5 and 2.5, and without it would have been 4, because you'd missed the half plus the half. This is faster and easier than any other fractional data type. It's just really handy. However, there are different disadvantages with this type up here. If you notice, you know, if your number has a whole bunch of zeros over here, and you could actually represent this number here with like 3 bits. You wouldn't have to take all of those bits to do that. So, you know, you can imagine that there are times when you want to go further this way or further that way, and maybe you know, those times you don't. There's times where you want to go both. You want to have bigger here and bigger here, but there most of the time you just want to go further one way or further the other way. You know, like if you had a number that was less than 0.01625 or whatever the number was we looked at, the smallest number you could go, 2 to the minus 6. Then you would want to, you know, shift your fixed point. You wish your fixed point wasn't shift right here at 6 digits. You'd probably like it over here at 8, or, you know, maybe way over here somewhere. So to come up with a way to get around this problem and more efficiently use the bits that we have to represent larger or smaller numbers, we use this thing called floating point. And it works nicely for numbers that have a lot of digits, like pi, e, a square root of 7, you know, irrational numbers that you really like to have tons and tons of digits. Actually, they have infinite number of digits, but, you know, to get the most accuracy, we want to get as many as we can, and we don't want to waste any of the whole number part. You know, if you like pi only needs 3, so that would have been just 2 digits, 2 binary digits, and then there's a whole ton of numbers after the you know, decimal point, 0.14159, whatever, you know, and all those numbers you'd really like to make those get as many of those as you can. And if you have to arbitrarily fix where the decimal point is in your number, it might not be optimum for pi. It might be more optimum for, you know, 10,000 or something. So the way we do that is we use what's known as floating point. And you got to remember, computers use a base 2 representation. They cannot be precisely represent certain exact base 10 numbers. So even if it is a you know, a base 10 number that you could represent exactly in base 10 digits, that doesn't mean you could represent it exactly in base 2 digits. It might go on and on forever. So there are some, you know, funny things like that. You're probably used to that in base 10, you know, like 1/3 is, in base 3 that could be represented with like 1 digit or 2 digits or something. But in base 10 it's you know, it's 0.333333, and it goes on forever, right? So fractional quantities are typically represented using this floating point form, and the way it works is your number equals -1 to a sign bit. So we're going to store this sign bit, and then that's multiplied by 1 point, and then there's some fraction here, and then that's multiplied by 2 to an exponent number which we subtract 127 from. So the number that's actually stored in our floating point thing is exponent and fraction and s. We don't really need to store this 1 here because it's always there. And so this 2 is the base, and this fraction is called the mantissa, and that's, of course, s is the sign bit. So s equals 0 means positive, and s equals 1 means negative. So you can represent negative, 0, and positive numbers with a fraction, and the decimal point moves to the very best location. So this is a binary scientific notation. Instead of 10 to the something, it's 2 to the something. This was all explained in the IEEE floating point standard for, you can do 32 or 64-bit floating point. The exponent is biased. In other words, they subtract 127 from the number that's stored. 127 is 2 to the exponent number minus 1, and then subtract 1. So the implied leading 1 in the mantissa is not stored, and 0 is represented by all zeros, and you can actually have a couple unnormalized numbers like infinity or not a number, if you divide by 0. So let's look at how this would be stored. Here's how it's stored. There's actually 23 bits plus 8 bits plus 1 bit, so that's 32 bits. So this is a 32-bit floating point number and how it's stored. The lowest 23 bits, the fraction is stored. The next 8 bits are the exponent, which remember you must subtract 127 from it, so it's 2 to the whatever this is, the e minus 127, and the sign bit, it's 0 for positive and 1 for negative. And you can see the number is minus 1 to the s times 1 point fraction times 2 to the exponent minus 127. So that's the way you interpret that 32 bits of data there, which is actually 4 bytes. So let's remember something about scientific notation. It will help us understand how to take a regular decimal number and express it in floating point. If you remember, 0.00123 times 10 to the 3 is 1.23. And 0.01230 times 10 to the 2 is 1.23. And 0.123 times 10 to the 1 is 1.23. So let's look at that same kind of thing in base 2. 0.011 in base 2 times 2 to the 129 minus 127 is 0.375 times 2 to the 2, which is 1.5. So that's you take this 0.011 and you turned it into 0.375, and you can also do, shift the thing over one more and so on, the similar way, and just like we did in base 10. So let's look at how we do this floating point normalization. So you shift, the fraction is shifted to the left. Remember, the thing to notice here is that when I change this number right here to a lower number, I need to change this guy by shifting it over. So this is really basically related to the shift number here. So remember, the fraction is shifted to the left. You decrement what you do is you decrement the exponent until the number is greater than 1, and then the 1 is dropped. That's what we do to do this. So you take your number. Let's look at an example probably. This allows dropping, not writing the 1, allows for one more bit of precision. So the 1 is assumed and not stored. And, this business, when you go down, it goes left, and when you go down, it goes left. So let's look at this number right here and try and understand what does this represent in base 10. This is a scientific notation number. So first of all, this 0 means it's positive. This exponent, which is 128, so we're going to say it's going to be minus 1 to the 0, which is 1, times 2 to the 128 minus 127, which is times 2, and then the number is 1.1. So 1.1 times 10 to the 2 means we shift this over by 1, and we get 1, 1. So the number is 3. 1, 1 in binary is 3. So let's look at another example here. Well, here's the work for what I just told you, and you can see how that works. See, here's the positive number, makes it positive. This is the exponent, which this number is 128. Remember, you have to subtract 127. That gives you 1. And then, remember, this 1 was implied, so you got 1.1, and I have to multiply that by 2 to the 1, right? So I get 3. So here's another example. Let's try this one. Okay, so it's negative. The exponent is now 2 because it's 129 minus 127. And then the number, the mantissa, is 1 point and then 10101. 1.10101. Okay? And so what is that number? Well, that's 1 plus a half. That's this 2 to the minus 1 plus an eighth, and then plus 1/32, which is 2 to the minus fifth. So you got this number right here, and you have to multiply it by 2, so you get minus 6.625. So here's a quiz for you. See if you can do these floating point to decimal conversions.